All right. Well, thank you to Alex and Klaus and Olaf for inviting me into this session. I am delighted to get to talk about some older work on the topic of generative models of the human connectome. And I'm going to do the terrible thing and start out with a rather cynical view of network neuroscience. And I know it's hypocritical in some way, but I'm going to start out like this. I'm going to start with the claim that network neuroscience, not always, but in a lot of cases, is a descriptive science, at least as we're using network science in neuroimaging now. And I think it's okay, but it's important to recognize this, right? Network neuroscience is giving us ways of talking about and describing features of networks at the level of their nodes, individual brain regions or connections. We can describe the network as a whole, things like scaling exponents, features like small worldness, controllability, synchronizability, and even intermediate scales, talking about communities, participation, modularity. We describe networks, we describe the brain a lot. And that's good. It's been really productive, after all. We can use these descriptors to tell us exactly how much of some feature or some property a brain has, and then we can use those amounts or those features to determine what's different between individuals, between groups, figure out what network descriptors are correlated with our favorite cognitive and behavioral metrics. And it's to the point now where there's this kind of like boilerplate network neuroscience study. I review a lot of them. You've probably seen them. I've written them. You've written them. But it involves taking networks from some control group, networks from your favorite experimental group, computing your descriptive statistics, t-test, write the paper. It's an oversimplification, but this is kind of the flavor that still abounds. And maybe it's not problematic, but I have some issues with the way this approach has gone up till now, right? We're neuroscientists, we're psychologists, we're cognitive scientists, we're imagers. We want to understand the principles by which brains are organized. We don't necessarily just want descriptions, right? And so if we want to understand those architectural principles, we don't want our descriptors to be conflated with one another. We don't want to misidentify those principles. And so one of the issues is that all of these descriptors, they tend to be correlated with one another. Networks that have modules, networks that have hubs, they tend to have a whole set of other features. And I'm sure Miko will talk about this in much more detail. But that makes it very difficult to determine what these fundamental architectural principles actually are, right? There's so many features that always go together. So that's the first problem. The second issue is that ultimately I think we also want to understand processes and function. We want to understand how brain networks work. We don't want just a description of them, right? Like imagine you had a car or an automobile and you had a list of all of the parts that go into that car. Could you somehow figure out how the car actually works, how all of the gears and widgets intermix to propel the car down the road? I know I couldn't, but I'm not an engineer, so maybe somebody else can get that from a list of those features. But all the descriptors we use in network neuroscience are kind of analogous to that, right? They're structural descriptors. They tell us all the parts of a network. So we have some problems. So how do we change this? How do we go from a descriptive science to one that emphasizes process, one that emphasizes network function? I'm going to claim that one approach, maybe not the definitive approach, but one approach is to use what are called generative models. And in this context, a generative model means a simple set of wiring rules that when iterated produce synthetic networks, and ideally these synthetic networks will have all the same properties or some set of properties in common with your real-world networks, with your brain networks in this case. And the idea is that if we can understand and identify the wiring rules that can recapitulate what we see in the brain, we can get deeper insight into the mechanisms that are responsible for creating brain networks and shaping them. So rather than coming up with descriptors, we want to understand how networks grow. What are the principles by which new connections form, new regions or new areas are added to the network? What are those principles? Is essentially what we're trying to do with generative modeling. We're trying to come up with simple descriptions of that process. And there's lots of reasons why we might like this. There's lots of advantages to generative modeling. On one hand, it helps us understand and tease apart which of those features of our brain networks are incidental and which ones are actually embedded in the wiring rule. So if we see a network that's modular, efficient, has hubs, small worldness, unless those features show up in the wiring rule, they're incidental. They're the byproduct of some other principle. So we can tease those relationships apart. Generative models, as you'll see, tend to have parameters. They're parametric. And so if we wanted to keep doing what we're doing, we can extract those parameters from the generative model and correlate those with behavior, t-tests between groups. We can do classification on the basis of the synthetic networks that the models generate or the parameters themselves. What I think is most important is that generative models, network generative models in this case, give us a way to make predictions about future states of a brain. Right? So if I have a good model that describes how my network should grow, and I know where that network starts out at time 0, I can give you some prediction. I can make with some amount of uncertainty, I can try to guess where that network's going to be at a later time. And that's important if we want to study disease, for instance, because maybe, depending on where you start, you could end up in a maladaptive or unfavorable state versus a favorable. And we can also begin to try to identify the kinds of perturbations that we would need to do to move somebody from that unfavorable trajectory back to a favorable one. So there's lots of reasons why we might like generative modeling. And I'm going to walk through one now fairly outdated application, but it was a first start for us. And this is a paper that came out in 2016 in Neuroimage. There's a long list of authors. And in this paper, we used generative models. We applied generative models to 3 independently acquired structural connectivity data sets, all diffusion imaging. And in total, the number of subjects were about 400. HCP, the NKI lifespan sample, and some data that was collected at EPFL. And our approach worked something like this. How do we use generative models with these data? Well, we tried to build models of individual subject connectomes. We tried to fit these models at the subject level. And we used a very specific class of generative model. It's a kind of growth model in which new connections are added to the network over time. And these connections are added probabilistically, right? So if we have our brain and there's some regions I and J, there is some relative probability at certain time step of those 2 regions becoming connected. That probability, it depends on their spatial relationships with one another, how far apart they are in 3-dimensional space. And also this, I'm going to call it a secret ingredient, but it's something besides a spatial relationship. It's some kind of topological relationship, and I'll explain a little bit more what that means in a moment. And so the algorithm works like this. We initialize an empty network with a certain number of nodes corresponding to brain regions, and each of these nodes have some position in space, x, y, z coordinates. And until we form some predefined or pre-decided number of connections, we will update those probabilities, and we will form one connection at a time, probabilistically. So we're going to do this iteratively until our network has some predefined density. And we're going to fit our model. We're going to choose these parameters, eta and gamma, by minimizing a particular energy function. And this energy function is based on Kolmogorov-Smirnov statistics. So basically the difference between cumulative distributions for node centrality, clustering, degree, and the edge length distribution for the network. So we have a model, we have a function that we can use to try to fit this model to observe data. So what did we find? Well, the absolute simplest case is where we actually throw away that topological term. So we just build spatially constrained networks. The only factor that shapes whether a connection should exist or not is the 2 regions' locations with respect to one another. So it's a spatial model. And this is an important model to test, first because it's the simplest that we can test, but also there have been a handful of papers in the last decade or so that have made really strong claims about the relationship of brain network organization and space. And these papers in particular make the claim that network organization, everything we observe, can be explained by distance dependence, a spatial relationship alone. So we're going to test that first. So this is what we get when we run our model. This is our energy function. There's only one parameter right now. And you'll notice that even in this simple case, there's a local minima, but it's not 0. So we're not getting a perfect fit. We're not even close to getting a perfect fit, in fact. Why might this be? To answer that, we'll look at some of the individual terms in that energy function. So this is the chaos statistic for the local clustering. It's the chaos statistic for the edge length. And you'll notice that they have local minima themselves away from, basically separated along this eta axis. And this eta, this is a distance penalty. When it's really big and negative, you're basically you're getting rid of all of the long distance connections in your network. You're forming networks that have no long distance connections. When it's really weak and still negative, well, you'll allow for some long-distance connections to form. So what's happening here with the spatial model is there's some trade-off. If you push it too far, you get no long-distance connections. If you push it too far the other way, you get no clustering. But there's no single parameter where we can get both. So the spatial model in this case is not especially good at explaining even these low-level features, these low-level distributional features of human connectomes. So if we make things a little more complicated and start looking at these two-term models, this is where we add this additional topological term, is what we're going to call it. And it's like the special ingredient. It's space plus this thing. And we can define this special term, this special ingredient, any way we like. We can define it in such a way that it matches well-known growth models like preferential attachment or homophily or degree assortativity and disassortativity. And so in the end, we test 13 different cases, 13 different definitions of this K term. And here's all the energies for all the 13 models we test. On the far right, that's our spatial model. Its energy is the highest of all models, meaning it performed the worst. Next is a series of models where this K term is based on relationships of nodes' degrees to one another, nodes' clustering coefficients with respect to one another, and then something about homophily. And the absolute best term, the absolute best definition for this K is something called the matching index, which is kind of like a network-level Hebbian kind of mechanism, where nodes that have lots of connections in common with one another, they're more likely to become connected at a later time. So that's the absolute best model. And what this model tells us then is that for the kinds of network organization we're seeking to explain, we can do it with basically two countervailing forces. One, that limits the number of long-distance connections in the network, some penalty on forming really long connections. This eta value is negative after all. And then we also reward the likelihood or we make it more likely for nodes to become connected to one another if they have lots of connections in common. So two simple rules can basically give us connectomes for free, kind of, which is kind of nice, I think, or it can explain a lot of features. This is the energy landscape, by the way, and these individual points represent individuals from one of the three data sets. Okay, so we can fit the model. That's fine. We optimize it to have a particular set of features in common with observed brain networks. But that's great, and it should have those features if we optimize it for that. But do our synthetic networks have other features that they weren't explicitly optimized to possess? And the answer is yes. Our networks, even though they didn't have to have these features, they nonetheless matched the path lengths, efficiencies, clusterings, modularity of the observed networks. So our synthetic networks have these properties kind of for free, which is also really neat. And then lastly, we applied these same models to a separate data set, and this is the NKI, which is a lifespan data set. And we found some interesting patterns in the model fits. First, so on the left, what I'm showing you is that the model fit is actually getting worse with age. This is a kind of standardized energy. I know it looks like it's increasing, but it's actually getting worse with age. And similarly, at the same time, coincidentally with almost the exact same correlation coefficient, the distance penalty is getting weaker. It's getting less negative. So with age, it seems like there's some different kind of wiring rules, some different kind of organizational principles that take over later in life. We're speculating on that, but that's what our data is bearing out at the moment. So I have a minute left, and I'll give you a quick summary. I am proposing that generative models are a useful tool for the network neuroscientist. They fundamentally shift focus away from descriptive statistics and onto the processes that maybe gave rise to networks and maybe created the networks. We show that pure spatial models, which have been argued to be sufficient for explaining network organization in non-human and human connectomes, it misses out on lots of important low-level features. So at least with the data we're looking at, it doesn't seem like they're good fits, the pure spatial models. On the other hand, spatial models plus this magical homophily term, this magical Hebbian-like term, are capable of reproducing many of the properties of real connectomes. We find some effects with age, but there's a lot of work that needs to be done before I'm confident in those. In particular, all of the models we test, they're stylized in some sense. They have a neuroscientific flavor. but they're not really grounded in biophysics. They don't necessarily match true developmental or maturational trajectories. So this is just highlighting the need for something like ABCD or other longitudinal data sets that allows us to suss out some of these more biologically plausible wiring rules. And then finally, I'll mention that we wrote a review on this topic now 2 years ago. It seems hard to believe. So if you're interested in generative models at all, a lot of what I'm saying here and some of my thoughts, along with Danny's thoughts, are in this review, and I'd encourage you to read it. So I want to thank my collaborators from all over, and I realize I've missed some people on this. I apologize. And if you have any questions, don't hesitate to contact me. And we're also looking for graduate students starting next fall, actually for the next fall, but apply this fall. So that's all. Thank you.